Good afternoon, everybody. I know immediately after the lunch, my responsibility will be to keep you awake. Okay. So today I'll be talking about this: how to design the high-performance, scalable, and converged middleware for the modern HPC and AI systems. I've been working in this area for almost like 35 years. So I'd like to try to give you a very high-level objective. If you take a very broad look, almost like 50 years back, scientific computing started, then the big data analytics came, and of course we are in the exciting AI world. But one thing is also changing. What I try to focus on, something called a computing continuum. You must have heard of that term. If you see the left-hand side, this is kind of the traditional model where the data is centralized on the file systems, and then you are trying to do the compute and the AI. But the right-hand side is the modern day, when data is not static at one place, it is continuously coming. Data could be coming from sensors, data could be coming from edge devices. You have to move the data or some results to cloud or HPC center. So this is the computing continuum. And one such example, a motivational example I'll give a little bit later, think of like a digital agriculture. Of course, agriculture has been there since the mankind was born, but can we really use AI? So think of a very large farm. If there are some diseases are happening, of course you can go manually, but you will have a lot of time and energy to actually look at it. Now the thing is, can I convert this to an AI problem? Like for a given crop, and let's say with the different types of diseases, I can actually build an AI model based on a lot of images, and then I can put that model actually on a drone, and depending on whenever I want to inspect my field, I fly that drone. And depending on the capability of the drone, the AI model can sit there. It can also do the inference. Or if there is not enough compute or memory, it can actually send either to edge devices or to the cloud, and it will give you the results. And then I can take these results, either feed it to some advanced drone or even to the tractor to go and precisely spray wherever the diseases have happened. So like this, I'll try to show you this a little bit later on. Like this is the Icicle Institute, AI Institute, which I lead. So we are taking in that institute a lot of these kind of challenges, saying not just develop HPC and AI software environments, but really utilize it for a lot of societal challenges. So the broad challenge here is that how do we design this high performance and scalable middleware while taking advantage of these all heterogeneous resources, together with also computing continuum. So I'll try to touch base a little bit trends in networking technologies, go to this MAPIC MPI library project, which I've been doing for last 25 years, and then bring some of those ideas also into the AI world, and then I'll finish it with the NSF AI institutes. So as most of you know, we're in an exciting field. Continuously better and better technologies are coming up. And irrespective of what application we run on the top, either HPC or AI or big data or data science, we need performance along these two dimensions. Scale out, that means more number of nodes, I want to get the best performance, and also scale up, that means within a node, if I keep on adding more CPUs, GPUs, XPUs, whatever you name, the performance also should increase. And most of you are familiar, like with the scale out, as we see, this is like a November 2025 thing. Left-hand side is saying, okay, these are the kind of in number. InfiniBand is like a 55%, Ethernet is 34%, but when you go to the right-hand side, you see it is flipped, because in terms of performance, there are a lot of these systems like slingshot-based systems, the top ones, which are changing the ratio. But this is a very interesting trend. I presented that yesterday in one of the sessions. So what I did here is took that number, the number of systems using InfiniBand and high-speed Ethernet, and over a period of time, what has happened. So it's a very interesting trend. So last 10 years, if you see, so this is where actually the InfiniBand was very high in the beginning, and Ethernet was not good. But then many of you might be knowing this RoCE came, RDMA over Converged Enhanced Ethernet. So that reduces actually the latency. So that means now the Ethernet became more attractive for some of the HPC systems. But then it continued, as you can see, the InfiniBand went down a little bit, Ethernet jumped up, but now there is actually a flip is happening with respect to AI demand. And with that AI demand, as you can see, again, the InfiniBand is going up because it is able to deliver a lot of bandwidth. Of course, there's a lot of action taking place. In this conference, you must have heard of ESON and Scale-up Ethernet. And especially the right-hand side, if you see, this just like moving from June to November, you see actually the Ethernet has again started coming up a little bit. Of course, InfiniBand is also growing, so we need to wait for another 2 or 3 of these top 500 lists to see whether there will be any flip here or not. And those are like the scale out, and of course, in the scale up, a lot of things are happening. NVLink from NVIDIA is the dominant one, CXL came. There are some solutions, but it's so-so at this time. AMD has introduced UA-Link. Then, of course, I mentioned about this Ethernet for scale-up networking, ESON, which was introduced at the OCP summit, and then also Broadcom is pushing for this scale-up Ethernet. So irrespective of whichever technologies come, now if I want to go into the middleware layer, the idea is that we need to provide whatever the middleware layer should be able to take advantage of the scale-up and scale-out. Okay? So that's what I'll be talking a little bit more. And especially, I'll introduce this with the MAPICH MPI library project. How many of you are familiar with this, MAPICH MPI library? Some of you, okay. So we started this project actually on almost day one of InfiniBand. When InfiniBand was introduced in October 2000, hardware was there, but there was no software. So we were in the very first group in the world to really come up with a high-performance MPI library. It was named as MAPICH. And we demonstrated it at Supercomputing O2 23 years back. And that time, I remember we were struggling to build even an 8-node InfiniBand cluster. But we have come a long way since 2002, and I'm very proud of my team. So this project has been continuing for 25 years, and now we support all the interconnects. Okay, you name any interconnects, HPC interconnect we support, any combination of CPUs, GPUs we support. And if you see the right-hand side, currently is being used by more than 3,500 registered organizations. And more importantly, just last week, we crossed 2 million downloads just from our website. Of course, our stack is also a part of Red Hat, SUSE, OpenHPC, SPAC. It's very difficult to keep track, but just from our website, that is the kind of things we crossed. And here you can see like how the downloads have been going up over the years. But more importantly, this is the architecture. So we started this architecture long back. If you see the left-hand side is the networking features, the right-hand side is the multi-core, many core. The middle one is actually our innovations. We come up with research publications. Many times we have those publications have initial results with different technologies. And in 3 to 6 months, we actually convert that into our production quality software. And then we were focusing on the MPI in the beginning. Of course, the PGAS also is supported. But now what is I'll be trying to show, not only we support the HPC, but the same MPI-driven stack, we can actually use it for AI. We can use it for big data. So that is where we are trying to push this converged software stack. So the motivation is like this. If you think of an MPI library like a MAPICH, we support all the CPUs, GPUs, DPUs, interconnects, while taking advantage of both scale up and scale out. Now the question is, in addition to having the HPC, can I actually run AI on this, big data on this? So that's what is the kind of the converged software stack. If we can design that, then we'll provide scaling and performance portability. But more importantly, we can also provide vendor neutrality. So now if you take a look at the commodity clusters, here you will see like a 3 CPU types like x86 Intel, x86 AMD, and ARM. Primarily like 4 interconnects, Slingshot, InfiniBand, Rocky, and OmniPath, and 2 kinds of GPUs. So if you do a quick math, you will see like 24 different combinations. Now, of course, we want to provide the best flexibility for the end user. They can actually choose any combination based on their budget. But then many times what happens is the vendor doesn't want to provide all those combinations. The vendor will say, okay, I'll provide you only for this CPU, this GPU, and interconnect. So this is where we are trying to make sure that we deliver a very high performance stack, and not only for like the unified support for on-premise and cloud. So this is our very latest version. If you're not familiar, please download MAPICH Plus 4.1. It supports the MPICH 4.1 standard. And it supports also both OAFI and UCX. Those of you who are familiar, this networking world has bifurcated now. Earlier, it used to be a combined open fabrics. So there are 2 ways. Some vendors are supporting OAFI and some vendors are supporting UCX, but we support both. So our stack can run on any combination of the interconnects. And then that's what we saw here, like a major CPUs, GPUs, and HPC. So then what we have done, that is our base package. Now you can think of these are the plugins. And that's what I'll be talking a little bit, like MPI for DL, for deep learning, MPI for QML, for machine learning. Even MPI can now, MPI for Spark. You can actually run Spark over MPI. And similarly, like a data science like Dask, you can run. So that's how we are trying to envision this kind of converged software stack. And as we are trying to develop these things, even within the MRP's project, also there is a sub-project which is called OSU Micro Benchmarks. Many of you might be familiar. These days, if you see any papers, always like they compare different MPI library, different interconnects or CPU, GPU. There is a micro benchmark which is called OSU Micro Benchmarks. It's very extensively being used. And not only like for research publication, a lot of tenders, bidding, procurement. In fact, you will see also some line items saying, please report the numbers with OSU Micro Benchmark. So we are trying to standardize this community, how people can present these numbers. So I'll just show you some sample performance numbers. I may not have time just to show that we are a vendor neutral stack. So the first one is like on a frontier. You will see AMD CPU, AMD GPU, and Slingshot. The second one is the Vista. At the Texas Advanced Computing System, it has a Grace Upper, NVIDIA GPU, the Grace ARM CPU, NVIDIA GPU, and InfiniBand. So here again, like these are some OSU Micro Benchmarks numbers. If you take like the basic latency, lower is better. Bandwidth and bidirectional bandwidth, higher is better. We are able to beat Cray MPH, which is the native version of the MPI library on the frontier. Similar kind of things like here, there is the point-to-point. This is like the collectives. As you know, the collectives are becoming also very important these days, not just for HPC, but also for the AI workload. So here you can see all reduced number, we are able to deliver the best compared to even Cray MPH, and also because it's an AMD system, it's a AMD GPU, we are doing also far better than the RECL. Same thing also holds good here. This is like a Vista, which is a InfiniBand NVIDIA system. If you see here, like all reduced, up to 256 GPU, we are trying to show here like a small message, medium message, large messages. Uniformly, we are able to even beat the NVIDIA's nickel version here. And same thing, another collective like you will see all gather. So like this, we continuously optimize all these point-to-point as well as collectives so that you get the best performance as an end user on any kind of a combination of CPU, GPU, and interconnect. And that's where we want to push our stack as a vendor neutral stack. Now that is again a very short overview of the MRPH, but then we are taking this idea and trying to convert it into the AI workload both for training and inferencing, which is called the IDEAL project. Now, if some of you are very much familiar with like the machine learning stack, you will see typically like you run, let's say these days is mostly the PyTorch, that is the right-hand side, which is becoming the more dominant kind of a middleware. And then below that, you will see Torch Distributed or Deep Speed. Different organizations have these stacks or the components. And then below that, you actually call the actual communication. Okay? So if you take a look at the nickel stack from NVIDIA, so they take the Torch Distributed and then push it to the nickel. You go to the AMD, they push it to the RECL. So what we have done, we have actually pushed it to MPI, our MPI. And so we have a PyTorch fork, and then in fact, we tried to contribute it back. There were some more business decisions. They didn't want to take our patches, so we have actually pushed it to our own GitHub. You can actually download. This is the very latest 2.9.1. And if you see, this is what like our IDEAL 2.2 release. You can see all the features. And it is like a 2.9.1 and also backward compatibility. And it has been tested once again with all CPU, GPU combination. Now, if I show you some numbers, so this is actually taken on the TAC Vista. Actually, it is running a DDP training. It's a GPT-2 model training using Nano GPT. If you see the left-hand side, like a 1, 2, 4, 8 nodes, you don't see much difference. But look at the right-hand side. Okay? So as we keep on like a scaling, our purely MPI-driven solution is delivering far better than even the nickel-based solution. The same application, you don't have to change anything. Instead of like the nickel-based runtime, you use our PyTorch fork and then the MRPH, and you will get this kind of performance. And same thing also happened. This is on the frontier. Very similar idea again, like a left-hand side are small GPUs, but as you go on the more and more number of GPUs, you see the difference. So this is where we are trying to make sure that we are actually optimizing not just like the point, but also the collectives. so that the both world can actually take advantage of the API communication. We are also like, that is the training, but these days, as many of you know, there's a lot of focus on inferencing. And a lot of research is taking place in the inference. I mean, imagine like a ChatGPT, millions of such requests are being hit with the server, how you can actually optimize the response time. So I call it like, those of you like the traditional HPC people, we used to have something called a high throughput computing, HTC. So now you can think of that HTC concepts are gradually coming back in terms of the inference, but the situations are very different. You have to use the GPU, you have to have the GPU kernels, the AI models. So this is where like I'm just trying to show one kind of work. This was presented in HPC 23. Instead of like doing a dynamic batching, which is very common, or doing a concurrent instances, we actually came up with this proposed temporal fusion technique. And through that technique, in fact, there is a software release here, but if you see here, we were able to almost give like a 16.7x speed up, okay? And this was in 2023, and once actually NVIDIA saw this design, they contacted us, we had some discussion with them, and broadly these designs have been incorporated now into the Tensor, the very latest version of the NVIDIA stack. Similarly here, another work we did together with Microsoft, like how do you train like an ultra long context language model with a fully pipelined distributor. So the broad idea here, if you see, on this side, if you see, when you are trying to go for the long context, and when you are trying to do this kind of training, the GPU utilization goes down significantly. And this is where you will see, like we did some analysis, and you see only like a 38% GPU is being utilized. I'll not have time to go over all the details, but we proposed this MLSys paper last year. We came up with this fully pipelined distributed transformer, and here you can see like we are able to push it up to even 57%, okay, by modifying how the transformer design is done. So these are just like a snapshot I'm trying to give, saying a lot of this kind of knowledge, whatever like from the HPC field, now you can actually come back to the AI field and redesign those stacks, because most of the time the AI people in the AI community, when they're coming, they don't have a lot of experience with the HPC stack and how things work. So this is where the convergence of HPC and AI field is happening, and you can come up with better and better solution. Now let me then, I have like around 7 minutes left. I can talk to you a little bit about that computing continuum, okay? Well, what I motivated earlier, saying that, okay, when you have all these kind of a drone, sensors, how do you really bring AI concepts there, and how do we design those end-to-end solution? So the bigger challenge is the data movement and control. Like the drone example, if you remember, I gave the agriculture. So how do you really decide? I mean, where to store, where to run your AI model, where to do inferencing, where to do training, and you need to balance it with the overall architecture. So if you go down and trying to study any of these problems, not just the agriculture, let's say food distribution, or transportation, you name any of these applications where computing continuum is being used, these are all the challenges, okay? Like how do you do data collection, cleaning, model training, how do you build a model commons, how do you design the end-to-end workflow, how do you do the scheduling, how do you take care of privacy? So these are actually, when you are moving into real applications, you have to think in a holistic manner. It is not just like LLM processing or just HPC, that is not good enough. You need to think totally. And this is where our Icicle Institute sits in. And those of you who are not familiar, the US National Science Foundation has invested on 29 of such institute. Each one is like a $20 million, but each institute has a very dedicated focus. Like you can think of like AI for physics, AI for astronomy, foundational models, so like this. And our institute, which is Icicle, those of you who are familiar with NSF, we got funded through Office of Advanced Cyber Infrastructure called OSC. So the focus, our mandate here is to really come up with this cyber infrastructure end to end so that people can use, other AI institutes can use, or anybody else also can use. And so very simply, you go to the icicle.ai, and this is the QR code. You'll be able to get a lot of information. So the way this institute, we have been working, we just finished 4 years. We just had the review last week. We are on the 5th year. So below is the computing continuum, and I motivated a little bit on the agriculture, but we also have 2 additional representative applications: food systems, food distributions, and also animal ecology. So we chose these 3 different fields with different kinds of requirements. in the computing continuum. And the middleware is actually the Osaka cyber infrastructure. I'll go into details. So this is a very large organization, coast to coast. Many universities are involved. We have like 16 organizations, a large number of faculty, students, almost 125 people are working here. And OSU, Ohio State University, is the lead. I am the overall PI, but we have a large team. So whatever I'll be trying to show is like the team's work coming up. We have also gone global. We worked with IIT Mumbai, especially on the agriculture side, because the agriculture issues are the same. But the solutions are different, because what we focus on Ohio for a soybean may not be exactly working in India. There we have to adapt it for rice or potato kind of things. So there's all different models coming. So this is the overall vision kind of things. As you can see, we have been doing a lot of foundational systems AI. And then the middle box are the actual cyber infrastructure, CI for AI. Very interestingly, AI for CI. Okay, so that is also very big focus in this project, not just CI for AI, but how we can develop the next generation CI with advanced AI techniques. Then we have software architecture, explainability. Also, there is a big focus on privacy, accountability, and data integrity. And of course, we do this all in a co-designed manner. So within our iSchool team, we have many faculty and students. They are non-computer scientists. They are from the Department of Food and Agriculture, Ecology, Food Distribution. So this is where we are trying to work with them to understand what are their requirements to use AI, and how you can provide solutions to them so that they can actually adopt AI. So that's how we have been working in a very tightly integrated manner. And of course, I will not go into, as you can see, we have multiple thrusts. Within each thrust, we have sub-thrusts. Then within sub-thrusts, there are topics. So like this, all the 125 people are working together for the last 4 years. So I'll just give a little bit of just one example of the agriculture. So if you go into digital agriculture itself, there are so many challenges. Like a left-hand side is trying to show, okay, how do I do like a residue cover on soil surface, soil aggregate size? Can I actually use AI techniques for crop development? Can I find out whether the crop is emerging properly or not? What is the nitrogen deficiency, defoliation? So all these are problems which the agriculture community always struggle. Now the question is, okay, how we can use our AI techniques and provide solutions to the right-hand side. So what we have done, we have actually come up with a very generic workflow. And in this workflow, it's actually kind of a modular, configurable, and also it is a plug and play. So as you can see here, like a very 4 different kind of the batches: data collection, pre-processing, model training, and inference and visualization. So what we have done is, through a very generic unified architecture, this entire workflow is plug and play. So we don't want to give you like a one solution. The solution is there, but let's say you are as a researcher or a practitioner or a company, let's say you want to modify B7. It is left to you. You can download our stack and modify the B7 component only to have even better results. So that's how we are trying to enable this end-to-end workflow so that people can actually customize. And then we have actually done the complete kind of an end-to-end solution here with all different kinds of wired, wireless data, different kinds of actions in the firm. Excuse me. And it's actually the stack can actually run on all different tractors, all different drones, because we are trying to also use very standardized APIs. So here is a short video I'll play. I may not have time to.
The Harvest cyber infrastructure streamlines the entire workflow. From the Harvest website, choose data collection and create a new job. Select the compute system and enter the destination path for your files and hit submit. You will then be redirected to the OpenPass to launch a digital agriculture performance.
I'll do a little bit fast forward.
Now, let's turn data into results using R of AI and HPC. First, we define the weeds to be detected by entering the labels and their corresponding search terms and an appropriate detection threshold. Are now ready to perform the crop intervention. To achieve this, we upload the shapefile generated by Harvest to the crop intervention platform, either an aerial drone or a ground-based spraying system. Here we demonstrate the process of uploading the shapefile to an automated spraying drone. With shapefiles in hand, it's time to take action. The system guides the sprayer to the exact location of those pesky weeds, delivering spot spraying with unmatched efficiency. As shown on the map, the drone follows the routes marked in blue. The solid blue lines indicate the segments where spraying is required. The dot
So like this, actually, we have demonstrated it's end-to-end workflow actually runs. And we have actually multiple versions of this pipeline. We call it like an AI as a service. Is running one copy is running on San Diego Supercomputer Center, another Ohio Supercomputer Center. We are deploying one on the AWS. So we call it like a BYOD model. That means we don't want to even claim your data. You bring your own data and then actually interact with the system to build your model, do the data cleaning, do the training, do the inferencing, and you take back your results. Okay, so that is the kind of the environment we are trying to do democratized AI. So then if you go into this website, I just showed you only one such workflow, but we have workflows for many of these food distributions, animal ecology, almost like we have 114 components which have been released. And anybody can actually download and work on these. And through these components and the end-to-end workflow, we have a lot of collaboration going on with all the different AI institutes, centers. In US, we are also going global, like in India, UK, Australia. So if there are like a organization who would like to work with us, I am looking forward to the collaboration. So we can actually see what are your problems and how you can take advantage of our solution. So with this, let me conclude my talk here. You can see like as I indicated in the beginning, for all these kind of the next generation systems, and especially when we are going for AI for science and all, you need to take a holistic picture of the not just like the hardware, but also the HPC, big data, AI, data science, as well as the computing continuum, so that you can come up with a end-to-end solution. And that's what I tried to do it in a short period of time to provide you an overview of opportunity and challenges and present a set of solutions. And I also indicated about the NSF AI Institute activities. So with this, I'd like to close here. I would like to thank all our funding organizations, not only the federal, but a lot of companies we work with. But these are all my heroes. I just come and give a 30 minutes talk, but the work what we have been doing is actually being contributed by almost 100 plus people over the last 35 years. That is just my group, and this is the Icicle team, around 125 people. Okay. So with this, I'll conclude here, and thank you. If there are any very quick questions, I'll be happy to answer. I'm here until tomorrow afternoon. We can also do discussion offline. Thank you.